Hello, in this session of our tutorials, we are going to be focusing on a question involving center of mass, and it is from the Northwest Regional Mock of 2024. The question says ABDE, actually it is ABCD. From the diagram, is a uniform square of side A glued to a right-angled triangle BDC with BC equal X. Given that the center of gravity of the composite body ABCDE lies on BD, Roman 1, show that X equals A root 3. Hence or otherwise, Roman 2, determine the distance of the center of gravity from the side AC. Here we are with the diagram representing the question, and I would plead that you watch this video to the end, because in the course of solving, I'm going to give very important hints and tips on how to solve generally questions that involve center of gravity. The first thing in this question is that we have been asked to prove that the base of triangle DBC, the length BC, which is equivalent to X, is equal to A root 3. Just like in any other center of gravity or center of mass question, we are going to calculate that distance by taking moments about appropriate axis. Talking about moments, then, it is important to note that while reading the question, you look out for the mass of the lamina or the component parts of the lamina. If nothing is mentioned about the mass, then the question would emphasize on the fact that the lamina is uniform. If you read this question, you will see that word uniform there. It is not at random. It has a reason. The reason is that once the lamina is uniform, the mass is evenly distributed all over its area. And so it is easier now for us to calculate the weights of the component parts of the lamina. In order to do the calculation, then we need to first define weight per unit area. You can call it lambda. So weight over the area of the lamina would give you the weight per unit area. When you multiply this weight per unit area lambda by the area of each component of the lamina, you will then get the weight of that component, which, as I have said, is important in the calculation of distances using moments. So in order to track everything, I would need to draw a table. It's important so that your work looks tidy. On that table, I will need to partition it into the portion, the width, and then the distances from axis. We have the portion here, then the width of the portion, then the distance of the center of each component from the axis. So in the case of getting X, I'm going to use any vertical axis to arrive at that result. This is because X is horizontal, so in taking moments, I will make sure that the axis is vertical because the distance has to be perpendicular to the axis. That is why to calculate X, I would either use BD, which is vertical, or AE, which is also vertical. In using BD, there might be complications because any axis that would divide the lamina into two parts, one part to the left and one to the right, there will be the need that moments on one side are negative and the other moments are positive. That may bring complications. So going to an axis that is at the extreme would be the best practice. I would take instead the axis AE. So here I would say distance of the center of the components. I would need to take it instead from AE because I'm going to be taking moments about AE. So distance from AE, my chosen axis. Now in Roman 2, we have been asked to calculate the distance of the center of the composite lamina from AC. So AC is an axis, so I will also need vertical distances from that horizontal axis AC. I will label that from, meaning the distance of the center of each component from that axis. It is from AC. Now for the portions, we have the square, which is of side A. So there is the square. And we also have the triangle. And then lastly, we have the whole lamina, which is a trapezium. The square and the triangle have been joined together to give the trapezium. So I need to put the component parts first and end with the trapezium, because for the weight of the trapezium, I will simply add the weights of the square and the triangle in order to get it. So I start with the square. The weight, as I've said, would simply be the area of the square times the weight per unit area of the whole lamina. So area of the square is side times side. Each side is A units. So I have A squared, the area, times lambda would give the width of that square. For the triangle, it is a right angle triangle, and the base is X, while the height is the side of the square A. And so half base times the height would give the area of the triangle, then times lambda will give the width of the triangle. Now, in order to get the area of the trapezium, we can use the formula for the area of a trapezium, which is half the sum of the parallel sides times the height. But already we have these two areas, the area of the square and that of the triangle, can also add up to give that area directly. In adding the two areas, the area of the square and that of the triangle, I have lambda, which is common, into a squared plus half ax. So that gives the width of the whole lamina, which is in the form of a trapezium. The most crucial part in this question, just like in any other question involving center of gravity or center of mass, is the distances. This is where most students always have problems in calculations. Getting the distance of the center of gravity of each component of the lamina from the axis under consideration. So you pay attention again in this part where I'm going to be determining the distances of the various components from the axis under consideration. On this column where we are looking for distances of the component centers from AE, I'm going to start with that of the square. The center of the square is in the middle where the diagonals intersect, and the distance from that center to AE, just the square, don't look at any other part of the lamina. We are on the square now. The center of the square is at that intersection of the diagonals, and we are looking for the distance of that center from the axis under consideration. So the distance from AE is half of ED, which is A. So the distance from midway to AE would then be A all over 2. So I can now complete that section of my table. Distance of the center of the square from AE is A over 2. I move to the distance of the center of the triangle from AE. The triangle is here and the center is somewhere here. For a right angle triangle, the center of gravity of the triangle is said to be 1/3 the length of each side from the vertex at the right angle. So if I am here, I am looking for this horizontal distance first from the center of the triangle to BD. It should be 1/3 the whole distance from B to C, which is x. But we are not looking at the distance of the center from BD. We are looking at the distance of the center from AE. So the whole of this distance, since from BD to the center is 1/3 x and from A to B is A, it means that the whole of that distance should be A plus 1/3 x to arrive there. So that is what I will write under the distance from AE of the triangle. We are looking at the distance of the center of the triangle from AE. So it should be A plus 1/3 x. In the case of the trapezium, which is the whole lamina, the question has specified that the center lies on BD, for which we are now asked to calculate the value of x. So if it lies on BD somewhere here arbitrarily, then the distance of that center of the whole lamina from AE, my axis under consideration, would just be the side of the square A. So this distance would be A. We move to the other distances this time from AC. We have to consider each component of the lamina separately and get the distance of its center from the axis under consideration, this time AC. So we start with the square. The center was here and the distance of that center from AC. This time AC is a horizontal axis, so we are looking at vertical distances. The distance of the center of the square from AC then should be half of the height of the square, and the height is A, so that distance will still be A over 2. So A over 2. We move to the triangle. The triangle again, since it is right angle, the distance of the center of mass of the triangle from the axis AC would simply be 1/3 the distance BD, which is the height of the triangle. So 1/3 of BD, and BD is A. Now the distance of the center of the trapezium or the composite lamina from AC is what the question has been asking us to find. So that distance, since it is vertical, we can denote it y bar. We are looking for it. That is what has been asked in Roman 2. So now we can go to the calculations. In Roman 1, we are asked to prove that x equals A root 3. In order to get the value of x, then, since the distance x is horizontal, we are going to take moments about the vertical axis AE. So moments about AE, we simply have the moment of the square plus the moment of the triangle should be equal to the moment of the trapezium about that axis. Moment of square plus moment of triangle should be equal to moment of trapezium. Each time a lamina is obtained by joining component parts, you would calculate any required distances using the fact that the sum of the moments of the parts that have been joined must be equal to the moment of the whole lamina about the axis under consideration. So we then have that the moment of the square will be the weight of the square times the distance of the center of the square from the axis AE. So we have a squared lambda, the weight into the distance a over 2, plus the moment of the triangle about AE, and we have the weight of the triangle times the distance of the center of the triangle from the axis AE. So we have half AX lambda, the weight, into the distance A plus 1/3 X, and that should be equal to the moment of the composite lamina from the axis AE, which is the weight of the composite lamina times the distance of the center of the composite lamina from that axis. So we get lambda into a squared plus half ax into a. So when you observe all the terms, you see that lambda a is common. So I cancel lambda, cancel a here to have 1. So half will be in the bracket, a and lambda will cancel, lambda and a would cancel. And finally we have a squared over 2 plus half ax, when I expand half x into the bracket there, plus 1 over 6 x squared should be equal to a squared plus half ax. Now when you look at all the terms, half ax is common, and then we have that 1/6 x squared should be equal to a squared minus a squared over 2, which gives a squared over 2. So x squared all over 6 equals a squared over 2, and you multiply through by 6, you get that x squared equals 3a squared, so that x would be the root of 3a, or a root 3 as the question asks us to prove. In Roman 2, we are asked to find the distance of the center of gravity of the composite lamina from AC. So we are going to be making use of this column to get that required distance, which is denoted here as y bar. So to get that, then we take moments about AC, so that again the moment of the square plus the moment of the triangle should be equal to the moment of the trapezium or the composite lamina about the axis AC. So the moment of the square would be a squared lambda times the distance of the center of the square from AC, which is a over 2. So I get a squared lambda into a over 2 plus the moment of the triangle, which is the weight of the triangle, times the distance of the center of the triangle from the axis AC. So that gives half ax lambda into the distance of the center from AC, which is 1/3 a, and that should be equal to the weight of the lamina. So the moment of the lamina, which is the weight times the distance y bar that we are looking for. So lambda into a squared plus half ax, the weight of the composite lamina, times the distance of the composite lamina from AC, which is denoted as y bar. We have lambda a to cancel in all the terms, so lambda cancels here, a cancels to give 1 at the numerator, a and lambda cancel, lambda and cancel a from each of the terms in the bracket. So we get a cancelled, and cancelling a in a squared will cancel the square, a will be left. In the first term, a squared over 2 plus in the second term 1 all over 6 ax, and x has been proven in the question to be root 3a. That should be equal to a plus half x, and x is root 3a, all that y bar. So looking at the question critically, we can still cancel a from all the terms. So this a would cancel, this a would cancel to give 1, this a would cancel, this other a would cancel to give a, since it is a squared there. And finally we can multiply through by 6, which is the LCM, to make things simpler. So times 6 here will give 3a, times 6 here will just give plus root 3a equals times 6, expanding 6 in the bracket there, we have 6 plus 3 root 3 y bar. So on making y bar the subject, we have that y bar equals, the left hand side can be written as 3 plus root 3 bracket a. When you factorize a, then divide by the coefficient of y bar on the right, which is 6 plus 3 root 3, and that gives you the distance of the center of the composite body from the axis at AC. Thanks for watching, and if you are new to this channel, please subscribe and activate the notification bell so that anytime we upload a new video, you will be able to watch it. Also share this video to your friends and classmates so that they get to know more about the channel, which has a lot to offer as far as preparing for your exams is concerned.